like would end just because like people had like obligations around like 6 p.m.
Sure, yeah. Sorry about like going overtime a couple of times. Hopefully today we will finish it on time. Today we have basically lectures as usual. So we do not do live programming today. Okay. Let's start. Hi, everybody. We are going again to talk about assembly programming today. If you remember, so we started looking into assembly programming by doing some actual programming so far, which was somehow fun. If you remember specifically, let's go here. We started by starting from high-level description of the problem in a natural language format. This is what we call the specification of the problem, right? And then we moved down the stack. We transferred the problem description into some structured algorithm, the way how you as a CS students, you understand, right? So we somehow make it algorithmic to solve the problem. And then we transfer it to some sort of a program. Essentially, we wrote some C code to see how we could transfer or translate the high-level algorithm into this C code, which is higher level than assembly code. And then we translate the C code into some sort of assembly, specifically MIPS assembly. And for those who we discuss about this, but like to make it again super clear, when we say assembly, we have different ISA. Specifically in this course, we talk about that all of the tasks would be in MIPS assembly, right? A particular machine, and we have a particular ISA set of instruction for MIPS, but we have like sort of different type of assembly language. For example, ARM assembly language. We have like x86 assembly. We have LC3 assembly, right? So when we say assembly code, you have to again associate it with particular instruction set architecture that you already know, and you somehow understand what I mean. So again, to recall this stack, we started by problem, turned it into some algorithm. We wrote some C code, translated into MIPS assembly code, and now you somehow have a practical perspective what's going on like at a higher level part of the stack. And later on during this course, not in the next few weeks, we will elaborate on basically more MIPS assembly, and somehow programming, the way you should program to be able to solve more interesting problems and to write more complex algorithms. Because so far it's like more hello world, more very simple type of algorithm, but you need to be able to build on top of this and write more complex algorithm. But during the second part of the course, we'll go deeper. Specifically, we'll have some lecture about Macroarchitecture, we'll not discuss circuit stuff, right? Because those will be covered later on. But specifically, we will talk about more interesting stuff about, like, for example, single cycle macroarchitecture, multi-cycle macroarchitecture, some advanced, interesting stuff that when you want to implement a particular ISA instruction set architecture, how you need to think about it and what's going on below the ISA level. But that would be the second part of this course. For the next couple of weeks, we will still focus on mixed assembly and programming in general. Okay, do you have any question that you want to ask before we start into the detail? You're good? And one other thing that I need to mention tonight, I will post basically your first serious homework that you need to pay special attention. More specific, let me see what at least to give you some impression what you should expect to see. So you will get basically some detail about this first homework, which is writing some assembly code for the problem that I described here, right? So I explain what is the problem, right? And I also put some template that you need to understand. So I try to put enough comments so you understand what exactly needs to be done. But also beyond this, you have some code that basically checks, think about as a test case. So this runs some test cases once you wrote your assembly code. This would test whether you wrote it correctly or not. So it executes some test cases, multiple test cases, and then like it tells you whether how many mistakes you made, right? So there's instruction basically how you need to execute, and these test cases help you to debug and like see whether your program is working correctly or not. Okay. And again, this should be familiar for you, how you need to approach it, what tools you need to use in order to debug your program. But again, to remind you about this, I put some pointers here, right? How you need to start. But hopefully the procedure that I put in the course website would be explainable enough. And by now, I expect that all of you have at least have started to write some and doing some testing, right? This is the expectation that I have, right? But tonight, expect that you should receive some notification from Piazza that I posted. And please try to spend some time to solve this somehow relatively easy problem, but you need to think carefully, and you need to use most of the some of the programming construct that we have discussed in order to solve this task. This is relatively easy as the first programming task. Please do it independently and try to spend some time on it. And because this is a process that you need to do it in order to learn how to program. And as we will move on, you will see more of these homework. So this throughout this course, hopefully you learn how to write more complicated assembly code and how you need to think about when you're writing in assembly. This is slightly, as you know, different from high-level languages. So it requires some thinking in order to get used to it. Do you have any question? And if some part of this, again, is not clear, feel free to post your question if you want clarification or something on Piazza. And others don't expect to us to answer it. I would wait until other classmates see whether others can help, but try to provide some comments to the question that may come right to Piazza. So look for it. Again, this is a forum that you should use in order to learn from each other, help each other. But you should obviously solve independently because this is the only way you can learn. But should be fun, and then things become better as we move on. Okay. So today, again, we focus on LC3 and MIPS assembly programming. For LC3, again, to emphasize that this is a good way to see that even though the ISA of LC3 and MIPS are different, the way how you need to think about assembly programming, the construct that you have, the way how you approach both programming and debugging are more or less the same. So it should be the same for other, like ARM architecture, for x86, more complicated type of ISA stuff. RISC-V, for example, other sort of architecture that you might have heard or in the future, or if you are interested to know more about these. But essentially, like having these two again for programming, as we did before for explaining more fundamental construct, provide a way for you to build some insight that these are more or less the same. So if you do your programming in MIPS, it gives you some insight that you can do other stuff a lot easier if you're interested. Specifically today and the next session we'll focus on understanding some high-level programming construct. Already you should know about this, but we'll go into more detail about debugging, some conditional statements and loops in MIPS assembly, right? And arrays in MIPS, how the function calls work, the concept of a stack, and so on. So basically these fundamentals for both LC3 and MIPS. We start by LC3 and then we'll move on to MIPS later on. Hopefully you remember von Neumann model, processing unit, memory, control unit, input output. Now that you somehow saw some assembly program, you see that how these are coordinated when you write program, right? So like when you use a specific instruction, how things will get executed on this model. Like for example, when you use, we discussed that this syscall. So basically, this syscall is the way that you communicate with input-output through calling this utility that will be taken care of by operating system, and other instructions. How all of these for each instruction needs to be coordinated in order to execute a particular instruction in a way. So hopefully you have some understanding by now. We discussed about this FC3 at a high level for each individual instruction. We discussed about this instruction cycle from fetching, decoding, evaluating address, fetching operands, execution, and store results. You will see more of this when we will talk about macroarchitecture. But when we do programming, again, we don't typically think about like these individual steps in the instruction cycle. We know the semantic of each individual instruction. So when you write code, you don't typically think about like these individual steps, but you need to think about it when we want to implement ISA, when we talk about the macroarchitecture stuff. We already talked about this. Okay. Let's do discuss some programming stuff in LC3. And this is very easy. But again, this is a good reminder for you to again think about it in terms of assembly code. You already have seen this in high level like C, Java, whatever you have learned these algorithm courses that you already have passed. Should be easy for you, nothing very new, but putting into the context of assembly, that's a good thing to remind ourselves. In this case, for example, we want to write a program that adds 12 integers. And you have seen this, we did this for in MIPS, similar logic here. So these numbers are, stored in memory. Like in this case, we have 12 numbers. The difference is that if you remember the code that we wrote, you remember we wrote together this adding 20 numbers, right? It was 20. And summing them up. The difference is that in that case, we did not need to access the memory in order to retrieve, because we knew what are those numbers. These numbers was from 1 to 20, right? So we did not need to go to the memory to retrieve the actual numbers. We construct these numbers because we knew like we want to add 1, 2, 3, 4 all the way to 20. In this case, the problem is that we have 12 integers that are stored in the memory, and we need to retrieve them one by one and adding them together, right? So this is the contrast that you can make. So you need to go through different steps. This is a high-level flowchart of the algorithm. You start by initializing some of the variables, and you know that the variables that we can use in assembly code are these registers. So use, for example, R1, and in LC3, you remember, you have 8 registers. So you use R1 for assigning it the first address of the number. So basically, 3100 is the address of the first element in your array. Okay. So you assign it to R1, or initialize R1 with this address because you want to use it to read the memory address one by one. R3, also you initialize it to 0, and R2 is basically showing the size of your array. 12 is the size of your array that you have, right? So R3 is used for taking care of the sum, right? Because you sum them as you retrieve them. So is a basically variable that you use to keep track of this number that you sum them together. And then R2 is the number of integer that is left to be added. In this case, again, to emphasize, we know 12. In some cases, maybe you were asked to get this number from input, right? So then you need to call syscall. In this case, in LC3, you have a very similar instruction in order to communicate with input-output. Very similar interface you will see. But in this case, we know 12 is fixed, so we don't need to do that. So we use a variable to keep track of this, okay? Then you need to check the condition whether R2 is equal to 0 or not. Iteratively, you you deduct 1 from R2 until it becomes 0. If it is 0, then you're done. Basically, there is nothing needed to be added. So you already added all of them. Right, so this is a check, is a condition to check. And then if the condition is not true, this is the actual stuff that happens, right? So you retrieve the content of the memory, which is located at R1 here, put it in R4, right? And you see how this is important, how you get use of these registers in order to do the calculation, right? So like here you need another register. You cannot use like R1, R2, or R3 because like they are doing different tasks, right? So if you use them, you know what will happen, right? So you put the content of the memory in R4, and then you add R4 to R3 and put it in R3. R3 basically is keeping the sum, keeping track of the sum. So you add them, and then you increment R1 to go to the next memory address. and then you decrement R2, meaning that there is one less number to be added. So this is very simple, right? So so after you accumulate the integer value to R3, you do this simple thing. You increment R1 and decrement R2 in order to solve your task. So hopefully this is very simple. Yeah.
So the 3100 to 310B, like that's representing like 12, right? Like, cause that would be like the hex for 11, but like 12. But are we considering like the size of the integer, like as 4 bytes, or like would that be the case? And would the integer just be 1 byte in this case, or one? Yeah. Like, are we worrying about
that? That's a good question. So the integers, like in LC3, you know the memory size in LC3. What was the memory size? So it was 16 bits, right? 2 bytes. That was basically for essentially for at each memory address, right? So for example, 0x3100, like you have 2 bytes stored there, right? So this is one word. Next would be basically, again, same, right? So memory is linear. And you know whether LC3 is word addressable or byte addressable, how you need to get access to basically to the next memory address, right? So if it is word addressable, the next one is 3101, right? If this is word addressable, if this is byte addressable, so the next one would be, since you have 2 bytes, the next one would be 3103, right? We know in LC3 it is word addressable, right? So the next one would be 3101, the second one 3102, all the way to 31OB, which is 11, right? So we have memory address from 0 to 11. All the 12 numbers are located there. Is it clear?
Yeah, like the one integer would be 1 word.
Yes.
Okay, gotcha. That makes sense. Thank you.
I have a quick question, Professor.
Yeah, go ahead.
So because we're working in LC3 right now, and this is a 16 byte of memory program, or 16 bytes of memory for LC3, does that mean if we were to have, let's say, 13 integers instead of 12 integers, would we run out of memory for running the program? Because we also have the 4 registers for our math in the program.
Let me see whether I understand your question. So if you're asking if we would have, like, let's say, one more number in the array, instead of 12, 13, we would run out of memory. Why is that the case?
I was under the impression that LC3 was only able to handle 16 words total. And if we're using 4 of them for R1 through R4, then wouldn't we run out eventually in our program?
Not really. So essentially we have 8 registers, right? These are particular registers. that the register files are separate from the memory. In memory, you have like 16 bits, right? So it means that in total, you have, how many in total you have? From, like, imagine from 0 all the way to all of these 16 are 1, right? So this is like the start and ending of your memory. You know that obviously you have different sections in your memory. You need part of this memory for putting the instructions, right? Part of the memory basically is allocated for the data. But it is more than 16 number of more than much more than actually 12 number of words, right?
Okay, I think I understand now. So to put it concisely, that we have 2 to the 16 minus 1 different places in memory to work with, and each place can be 16 bits long.
Exactly.
Okay, that makes a lot more sense. I was confused on that for a while.
Exactly. I'm happy that you asked it. Thanks. Yeah, this sometimes become confusing, but thanks for asking. This is good. And the same is, in MIPS, but in MIPS we have larger memory because we have 32 bits, and then so it's much larger in MIPS. Okay. This is good. And this is like how the program is encoded in machine with 0 ones, right? Again, like this is like encoding of the instruction that we have. Obviously, it's not readable, but this is the way how it looks like when it sits on the memory of LC3, the instruction section, right? The text section. So you know what I'm talking about. These obviously you can go to the LC3 book and see what these instructions are. So for example, like the first one is load effective address, because you need to load the effective address of the memory, right? And do some calculation. We'll discuss it. Branch, adding, again, branching here, like how you need to interpret this, right? So for example, for load effective address, like what this means, right? But again, if you forget, you can go and check the instruction. Again, the detail doesn't matter sometimes. It is important to interpret this instruction correctly when you have the description of this instruction. This is what it matters. So let's go through these instructions one by one to make a correspondence with this algorithm that we discussed. And also, for example, for branching, what these 3 bits represent, right? So this is, that this was N, Z, P. So when Z is 1 here, means that this is branch 0. If this basically says that if this is 0, then it would branch to a particular location, right? Which is indicated here. So again, maybe you need some reminder what these instruction means, but let's go through them. Or for example, here is the same code, right? So you see the same opcode here. So this is branch, but you have all of them are one, meaning that this is unconditional branching. When all of these are one, basically this would branch no matter what. This is like branch NZP. So this is for like here at the end, you want to go back to the loop. You saw that this construct in the code that we wrote together. So it is similar. So the first one is load effective address. Again, you need to remember. So it puts here is the register. So register 1 is indicated. So it puts PC plus 1. PC is what is PC now? So basically the updated PC, when we are executing this instruction, means that the PC is incremented, right? So the PC is X3001, right? And here is the offset, right? So this is 0x00FF. So we needed to put X3100 into R1, right? And then what's going on? So so the machine needs to, so when you say that I need to load X3100 into R1, you know this, and this is the semantics. So you need to, the machine needs to calculate a number. When it is added to PC plus 1, it would result it into this particular value. And you know that how it happens, right? So PC is 3001. When you put them together, 00FF, hopefully you can see that when you align them. So again, it's easy, but let me do it quickly for you to make it super clear. But so what you had was 0x3001. So this is PC plus 1, okay? And the offset is 0x00FF. So when you add these two, so you know that this would be 0, right? And then you move 1 here, 0, 1 here, 1, 3, sorry, 0x, right? So this is the result of adding these two numbers. So this is again adding in hex. So that's why it works. So basically, your the machine produce this number automatically based on what address you need to go, right? This translation happens automatically. The LC3 does that. So that's how you can interpret this. But again, like probably you want to go back to previous lecture that we discussed the detail about this particular instruction if you want to remind yourself what's going on. But hopefully you see what I'm talking about here. And then the next one is to reset register R3. Again, R3 wants to keep track of these adding numbers, and you see that how we use AND to reset to 0, right? So we AND R3 with 0. When you AND whatever register with 0, the result would be 0. So this is the destination, which is like R3 itself, right? So we AND R3 with 0 and put it to R3 in order to reset it to 0, right? So you can follow the logic here. Also the same for R2. And let me know if this is not clear. I can explain it, but I presume you already know, right? ANDing, right, with 0, everything will be 0 as a result, will be reset. And then here we use add instruction to add R2, right? This is R2 with 12, right? So essentially we set R2 to 12. Previous number was 0, okay? And then here we check. This is where we are here in the flowchart. We check whether we want to branch or not, and where we want to branch. So we check the condition whether R2 is 0 or not, right? And if you remember the semantic of this, of branching, it considered the previous instruction, right? Previous instruction was like R2. When we go to the loop for the first time, R2 is 12. So obviously the branch would not happen because it is 12. But like we will see when it would branch, right? So the next one, so this is basically saying where we want to go, right? So branching, because we know that like when we are, so we want to go after the place where we are done with everything. We are done with the main stuff that is happening, right? So if you look at like the memory address, how many instructions we have? Like we have 1, 2, 3, 4, and 1 for branching up, 5. So the next place we want to go is after this. So it would be X30 OA. Basically is the next memory address here sitting below this branching, and this is what it refers to. Again, here you see 5. Why 5? Because if you add 5 to the PC plus 1 at this point is 3005. You add 5 to it, you get 3008. Hopefully this is clear, right? But let me know if it is not. So that's why, that's what's going on here. And then next point is you want to read the memory address. What is in the memory at R1, right? So here we load the content of the memory into R4, which is indicated here. It is within this like 3. Again, remind, like we have only 8 registers, so we only need like 3 bits. We discuss about this encoding. and how you need to read that. Okay. So essentially we are reading MR1, put it into R4. Next thing is also using and you know that like this bit indicating whether this number is signed or unsigned, right? So here we add R3 and 4 and put it into R3. So we have the number that we want to add to the sum. So previously we put it into R4, now we add it to R3 here, okay? And then next one we increment R1. And again, in this case, we use add, right? So we add R1 here to increment the address. And then we want to decrement the counter. So we decrement 1. And you know that this is when we have 1 in this bit, right? This means that this is signed. So you need to interpret this as a signed value. And hopefully, again, tools complement, you know how to interpret this. So this is -1, okay? So this is what we do, R2 minus 1, put it to R2, right? So these are the registers that you use for referring to this. And then at the end, you want to do the unconditional branch. So here, no matter like what is in R2, right? So we jump to we go back to this checking, right? So we want to do this checking right, no matter what, right? So this would take us to this memory address to 3004. And then here we check whether R2 is 0 or not. Yes, go ahead, Russ.
So is that like when you're incrementing the program counter, like, and you can choose how much you want to increment or decrement it, is that like a go-to statement where like you're jumping to that, or are you going through each next one until you reach it, or are you jumping there? Like, are you saying go immediately to that one? If you know what I'm saying.
You're talking about like branching, right?
Right. Like if you're, do you just jump there, or do you like, is it like, does it have to go through each one, or is that like a go-to kind of thing?
Yeah, you jump there directly, right?
Okay.
So basically this says that branch no matter what to where to PC plus 1 minus, right? So this is again 2's complement minus 6, right? And at this stage, when we are like here, PC plus 1 is 3008, right? So the incremented PC is 3008. Then minus 6 would be 3004, right? This is what you get. So this is taking you to this memory location, pointing that you need to execute this this instruction. So basically, this is like a go-to, right? So take you to this memory location in order to execute this this instruction. Hopefully, this is clear now, right? But let me know if you have question about this. And again, like here at this, again, we are here, right? So it checks again whether R2, right? Because R2 was the previous instruction, right? Whether R2 is basically 0 or not. if it is not 0, again, it goes through the same, here, load the value added to memory address, increment the address, and decrement R2. So after like 11 steps, after 12 steps, R2 becomes 0 finally. So when you do this jump here, this would check again, R2 is 0. If it is 0, then jump here right after this unconditional branch, and then like you are done. And then you have the sum of these stuff. Is this clear? Do you have any question or not? I think it's simple enough, but it was good to go through it to see what are the instructions that you need to use in order to implement this algorithm. And again, like this algorithm could have been implemented in different way, more or less. This is one implementation of this. Could have been like implemented like in some other way. You could have used some other alternative instruction in order to implement this logic in order to add these 12 numbers together. Okay. And this is like how the data path looks like in LC3. Somehow you should be familiar, but like in this plot, you have more information, more detailed information than the previous one. So it is more complete in terms of like what's going on, what is the interconnection between different elements, right? So you have input, you have output, you have memory. This is your process unit. This is your control unit. This is the bus. This is the multiplexer that you have for like memory address register, right? This is the adder that you need. These are the sign extension for addresses that you need for like when you feed it to the adder, and also this is sign extension for the stuff that you need to go through ALU. Some of these instruction you remember, like you need to sign extend, for example, the numbers, and you had some calculation, right, that you needed to basically do some compute, like to add two numbers, right, or add immediate to register value, right? So you need sign extension operand here, and you have this conditional code branch NZP, and these are like NZP values which are set. So basically these are the data paths, and the stuff that you have will again go back to this later on, but this is like, again, like all of this will be coordinated in a way that execute the instruction that you write for LC3. Let's briefly, I mean, we have 10 minutes to talk about some programming construct. And again, these are like some generalization. You are familiar with this, nothing much new, but hopefully it's a good reminder for you to think about, like when you want to implement stuff. So obviously programming requires dividing a task into some smaller unit of work. And the goal is to replace the unit of work with some known programming construct that represent the only part of the task, right? So like this is somehow can think about it as a translation, right? I want to use this particular programming construct, like if I want to use like do while, this type of particular programming construct here. Obviously, for implementing a task, you could use different programming construct, and like it really depends how you think. This is more efficient, right? So there is not only, there are numerous different ways of implementing a task. There are some basic, obviously, programming constructs like sequential construct, conditional construct, and iterative construct. These are like basic construct that you have when you're writing a program in general, overall, and you're familiar with this, right? So sequential construct, when you have a task to be decomposed, and then you can decompose it into like multiple steps that would be executed like one after another. So you need to finish the first part and then finish the second part, right? So these are like sequential task. And like if you think about like and this is like do the first part and do the second part, already you have seen this when we put sequentially, like for example, when we initialize a value and then we increment a value to increment a particular value of a variable, like in this case, a register value. Conditional construct is also you're familiar. These are like if type of or switch type of conditions where you need to test the condition, right? So we have like we test the value of R2 to check whether it is 0 or not, right? So the result of the test could be either false or true, and then depending on each task, each part, we have different tasks to execute, right? So if, like in our case, if the result of the check R2 was not equal to 0, then we had some task to execute. If you remember, we needed to retrieve a memory address, content of a memory address, and add it to some other variable. We needed to do some stuff. Otherwise, we needed to jump into the address right after the unconditional branch, meaning that like continuing with the rest of the program if there is any. So this is what's going on, but you're familiar with this. Depending on this condition, either you have a subtask or maybe do nothing, right? In our case, basically, it was do nothing in one way, essentially. And you have like you might have a if else statement, or like a switch case where you might have like different cases. Depending on the particular case, you need to execute different tasks. So basically, essentially, this could be more than two, right? So if this is switch case, depending on the number of cases you have different branches. Essentially, you have more than two branches, 3, 4, 5, whatever. An iterative construct is also when we have a kind of loop, right? we need to do a task or a subtask, a number of time could be a fixed number of time. Like, for example, when you want to use for loop, right? So in for loop, like, you know that like you need to like do this like 100 times, right? Or in do while, you want to do a task until some condition, right? So you test the condition. If this is false, you're done. If this is true, you want to execute this task. So this is like hopefully familiar for you. And you you can think about like a different construct, like for loop, while loop, do while. Hopefully these differences are known to you, and we already have discussed it, right? But you will see more of these through examples that we might have in the lectures, and also you essentially need to use all of these constructs when you solve the problem for your homework and so on. Let me see whether we should go through this example or not. Probably not. Let's go through this example next time, because I promised to finish it on time, so I don't want to go over time this time. I'm sorry about that. We went way over time a couple of times, but hopefully that was useful. I didn't want to break the whole track, but yeah, let's just stop it here. Look for the notification that you will get tonight for the homework, and make sure you submit it on time. But again, I want to remind you that think about the learning, right? You want to learn. And for me, it is important you get the best learning experience here. If you have any suggestion, you can suggest. But for me, like, the learning matters a lot rather than the grade that you get. I think that like you all should get a very good grade at the end, but like learning matters. Yes, Ralph.
When will the homework be due?
Sorry?
When will the homework be due?
That's a good question. Like that was the only thing I wanted to, because it was ready over the weekend. I wanted to like think like how much time I want to give it. I don't want to, like, I want to give you enough time, especially for this homework, to like think about it and like spend some time to try and, you know, to see. It's relatively easy. Probably you don't need more than one day, but I would like you to have until next week, you know, so you spend some time with it, and if like there is a need for giving more time, I'm happy to extend the due date. But again, like, this is since this is the first serious homework, that's why I would like to do. And again, like, learning matters. I'm not like very difficult instructor, so I would like you to learn as much as possible rather than being very strict about, you know, due dates and stuff. But sometimes it is useful to have a structure. Yeah. Okay. Any other question? Sounds good. Yeah, then thanks. Hope have a good evening.
Thank you.
Thank you.